let's do some rapid fire calculations with radicals and exponents. In this top one, we're asked to simplify a structure which is a subtraction. Now, like with x's and x squareds, we would want to combine like terms, which means we want to see if we can reduce each of the individual terms to some common foundational piece, which can then be combined across the subtraction. Let's see. Let's start digging for what that might be. I'm going to just take this 80x, and let's see, what might be a common factor between 80 and 45? 5. How about 5? So to get to 80, that's 16 times 5. Is that right? I believe so. And then over here, I'm going to leave everything alone, except I'm going to write 45 as 9 times 5. Like this. And then remember our properties of exponents, which are also properties of radicals, that the square root of a product is the product of the square roots. So the square root of 16 times 5 times x is the square root of 16 times the square root of 5 times the square root of x. And so I'm going to accelerate a little bit. Note that when I break off the square root of 16, that's just a 4. So 3 times 4 would give me 12, and then the leftover is the 5x. And then over here, similarly, this 4 is just hanging out waiting, but if we break the square root across the product here, the first item we'd see is square root of 9, which is 3. And so 4 times 3 is 12, and then the remaining bits are the 5x. We can't really simplify the square root of 5x. And then when we see what we've simplified to, oh my goodness, this first term is the same thing as 12 times the square root of 5x, and we're subtracting another term which happens to be reduced to 12 times the square root of 5x, and so we get 0. Well, that was surprising. In this case, I want to rewrite this quotient, which happens to be a mess. You have to interpret what rewrite might mean, but in this case we see a root sign and it's in the denominator, so maybe we would just like to reconfigure this so we're not seeing radical signs, we're just seeing what is the ultimate exponent on a inside all of this mess. Well, to do that, how about I leave the 4 in the numerator alone and recognize that the 7th root of a squared can also be written like this. Take that square, or take the 7th root away and write it as an exponent of 1/7. This can then be 4 over a to the 2/7. And if we would like this written as just 4 times a to a power, we do the reciprocal game. When we flip a to the 2/7 from the denominator up on top, we change the sign of the exponent, and so this mess right here is equivalent to 4 times a to the negative 2/7. Again, is this really better than this? I don't know, but we were asked to rewrite it, so what the heck. Here's another simplification, which just means hammer at it and cancel stuff you can cancel and so on. The first thing I'm going to notice is that if I take the constants off to the side and just leave the 225 and the 49 alone, everything under the radical is in multiplication, so I can rearrange. The 225 and the 49 are just now hanging out as a common multiple of everything else, which is x cubed over x, and x cubed over x reduces to x squared. And then it just so happens that we have 3 perfect squares under the radical. And just to emphasize that, notice I'm not going to try to divide 225 by 49. I'm going to recognize that 225 is something squared. Is it 15 squared? I'm going to go with it. 49 is 7 squared, and then we have times x squared. And all of those terms are having their square root taken. The big square root can be distributed across the multiplications and divisions here. So the square root of 15 squared is 15. The square root of 7 squared is 7. And the square root of x squared is just x. And maybe we tidy that up a little bit. There we go.